Hey, welcome back. This is the last section now in Chapter 9. Finally, we'll be able to say conclusively that we can use these power series representations for functions almost in place of the actual function. And in order to pull this off, well, I mean, where have we gone? So we have kind of backdoored a method for determining some power series. For example, the natural log of x plus 1 is equal to the integral of 1 all over t plus 1 dt from 0 to x. Okay. And is this going to be possible? Are we going to be able to figure out a way to kind of backdoor a representation for all these other functions like e to the x, sine of x, all that jazz? The only reason why we were able to get this power series representation was because of the geometric series, and we were able to kind of replace this with a power series. Okay, so in general, that's probably not going to be the best way. It turns out that, in fact, the method that we kind of learned with the Taylor and Mclaren polynomials will be the method that we'll use for producing the the power series representations in general. Okay. Okay. So first, we want to prove this. In order to prove this, we kind of need a helper theorem. I don't know if the numbers have changed. This used to be theorem 9.21, and it just says that power series are basically differentiable over and over on their interval of convergence. Okay, and of course there's issues at the endpoints, but on this open interval, they're good. So if power series has a radius of convergence big R greater than 0, then it's differentiable. You can take the derivative. On this particular interval, c minus r, c being the center to c plus r. Okay, so we need that in order to kind of do the proof for this next theorem, which is saying it all. Theorem 9.22. Basically, if f is represented by a power series for all x in some interval, some open interval, I, so if there exists some power series representation, it is formed in the same way that we formed the Mclaren and Taylor polynomials back in 9.7, I think. So if f is represented by a power series for all x in some open interval I containing our center c, then the coefficients of this power series a sub n will be of the form nth derivative of f evaluated at c divided by n factorial. Okay, and you can kind of read through the proof in the book. They suppose that there exists this power series representation, and then they're able to look at the derivatives and basically line up the derivatives to the coefficients. It's almost exactly the same thing that you see in the Taylor polynomial section for developing these coefficients. Okay, let's take a look at let's take a look at maybe something else, right? Let's take a look at how about the power series representation for 1 all over 1 minus x, right? So f of x equals 1 all over 1 minus x. We saw in the last section that this is the sum of x to the n from n equals 0 to infinity, right? And it's for absolute value of x less than 1. Okay, so what all of this is saying is that we can produce this power series. There's only one power series that's producible, and that power series is the same one we would produce doing this process that we learned in the Mclaren polynomial, Taylor's polynomial section. So let's do that process. So if you remember how that works, so let's find the nth degree Maclaurin. So remember, Maclaurin means it's centered at 0. Polynomial for this f of x, which is 1 over 1 minus x, right? Okay, so how did that work? We needed to list the function and its derivatives, and then along the other side, kind of evaluate them all at the center. And then along this other side, we're evaluating them all at 0. And of course, once we get all of that, we take the second column here, the outputs of that second column, and put them into our polynomials. So the way it would work, there would be basically, you could just fill in the boxes, right? So blank plus blank x plus blank x squared over 2 factorial plus blank x cubed all over 3 factorial plus blank x to the 4th over 4 factorial, on and on up to blank x to the n over n factorial. Okay, so let's get these guys. I'm just going to write this as 1 minus x to the negative 1. And of course, you put in 0, you get 1 to the negative 1, which is just 1. The derivative negative 1 minus x to the negative 2. And then the chain rule, we have to multiply that by negative 1. The negative 2 goes on the outside here. The derivative of 1 minus x is negative 1. Okay, so that's going to end up being 1 minus x to the negative 2. And of course, if you put in 0, you're just going to get 1. The next one, you bring down the negative 2. There's going to be a chain rule, so times another negative, it'll become positive, and you'll have 2 times 1 minus x to the negative 3. So that'll be 2. Then you'll have, and now I'm going to start writing it as factorials. You could write this as 2 factorial if you want, because 2 and 2 factorial are the same. But once you do the next derivative, you'll bring down a 3, so it'll be 3 factorial times 1 minus x to the negative 4. In other words, over here it's 3 factorial, etc. Right? Okay. So what do we have for the power series representation? So again, let me write that down from above so we can compare and contrast these things. So the power series representation for our f of x, which is 1 over 1 minus x, we're saying is the series of x to the n from n equals 0 to infinity. So what does that look like? Plugging in 0, you get 1, and then plus x squared plus x cubed plus x to the 4th, and on and on and on, right? Let's see what we're getting with our polynomial doing this method that we learned in 9.7. So copying and pasting this column over here, this 1, 1, 2 factorial, 3 factorial, 4 factorial into the boxes. We get 1, 1, 2 factorial, 3 factorial, 4 factorial, 5 factorial. Oh, that would be n factorial, right? So just this process repeating itself over and over and over, all the way up to the nth derivative. The nth derivative, judging from the pattern, it's going to just be n factorial, right? So 4 gives you 4 factorial, the 5th derivative gives you 5 factorial, the nth derivative, we'll say it gives you n factorial. Okay, so we can get rid of that and write n factorial. So what is happening when you reduce the power, the polynomial, the Maclaurin polynomial, you're going to get 1 plus x plus the factorials just divide away. So you get x squared plus the x cubed plus x to the 4th. In other words, you're basically getting the same thing that we got through our backdoor methods in 9.9, right? It's just our polynomial is finite, and this power series representation just goes on and on forever. Okay, so yeah, I mean that's kind of the point of theorem 9.22 right here. 9.22 basically, if you have a power series representation, it's going to be the representation formed by creating the coefficients of the power series based off of the derivatives and then dividing by n factorial all the way through, which is exactly the same process we learned in 9.7. Okay. Okay, so even if you do have some other clever way of figuring out the power series, it turns out that this method from 9.7 is the go-to method that we're going to be using. Okay, so hopefully that kind of makes sense. And at this point, then we can form basically the power series for any function so long as it has a lot of derivatives, right? So if you can't make these derivatives happen over here in this kind of construction, you're kind of out of luck. So that becomes a requirement for forming these series. Anyways, without further ado, let's go ahead and introduce the power series representations. So these are called Taylor. That's when centered at some value other than 0. So basically x equals some c value. And then Mclaurin, where it's centered at something other than exactly at 0, right? So that's the case when c equals 0. So these guys are basically just the f of c plus f prime of c times x minus c plus f double prime of c all over 2 factorial times x minus c squared plus f triple prime of c all over 3 factorial times x minus c cubed plus on and on and on, which we could write in summation notation, going from n equals 0 to infinity of f, the nth derivative of f, evaluated at c all over n factorial times x minus c to the n. Okay. Where c, if you put in c equals 0, you just get the Mclaurin series. But okay. Okay, so there it is in all of its glory. Let's actually now find some common Taylor series. For example, the Taylor series for sine of x. And let's make it a little more interesting. Let's find the Taylor series for sine of 3x. Okay, so the question will be find the Taylor Maclaurin series. Here we're going to be looking for a Maclaurin series, but find Taylor series in general. Series representation. Okay, so they will tell you your center, in this case is 0. So all right, so I need to get the function and all of its derivatives and then evaluate them all, and then I'll be copying and pasting into my sort of infinitely long now polynomial. So I usually just go down and make enough so I can see the pattern. Usually for trig functions like sine and cosine, and go down to the 5th derivative. All right. So anyways, over here I'm evaluating them all at 0. And then for the summation notation, I'm going to need the nth derivative if possible. So blah, 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 f the nth derivative Hopefully I can make that happen. All right, so derivative sine. Derivative sine is cosine 3x, and then the chain rule, you have to multiply by 3. Derivative cosine is negative sine 3x, and then multiply by 3 again. So negative sine 3x, derivative of that, negative 3 cubed sine, goes back to cosine 3x. Derivative again, it will become positive 3 to the 4th sine of 3x, which is back kind of where we started, and then you get 3 to the 5th cosine of 3x. Okay, figuring out f of 0 for each. This will be 0, 3, 0, negative 3, 0, 3. So it looks like there's even and odd guys in there. So I'm not exactly sure how to encode that into my nth derivative. So let me just look at the representation for this function and kind of fill in the blanks first. So blank plus blank x plus blank x squared over 2 factorial plus blank x cubed over 3 factorial plus blank x to the 4th over 4 factorial plus blank x to the 5th over 5 factorial plus on and on. So copying and pasting, the first one is 0, 0, then 3, 0, negative 3, 0. Whoops, and those have exponents on them, don't they? So this would be cubed, and then this would be to the 5th. So cubed, and then 3 to the 5th. I'm going to simplify that, so it's going to be 3x minus 3 cubed times x cubed all over 3 factorial plus 3 to the 5th times x to the 5th all over 5 factorial. And you can almost guess what the next one's going to be, right? It's going to be minus 3 to the 7th, x to the 7th over 7 factorial plus dot, dot, dot. So going into summation notation then, I think we will be able to do that. So sum, I'm going to go from n equals 0 to infinity. And the form is always kind of like 3, there's a negative 1 going back and forth, right? So first we're going to have a negative 1 to some power, and then we're going to have 3 to some power, and then x to some power, all over something factorial. Okay. Okay, and you can start at n equals 0 or n equals 1. I think 0 is the best choice for this problem. But anyways, the first term has to be positive, so that kind of tells you that this guy has to be just n. It's always going to be n or n plus 1. Okay, so it's n plus 1 if the first term is negative, if you start at 0, okay, right? Because the odd exponent makes it negative, the even exponent makes it positive. 0 is considered even, so you put in 0, you get negative 1 to 0, and you have a positive output. Okay. Okay, then you kind of look at these other things. So the things we're filling in the blank for, the first blank, are these guys. And you can almost pretend there's a 1. So you look at that as a sequence, right? The sequence there in those boxes is 1, 3, 5, 7, blah, blah, blah. That thing is an arithmetic sequence with a difference of 2. So if you have those arithmetic formulas down, a sub n will equal a sub, in this case I'm using 0, and then plus n times d. Probably in pre-calc you learned a sub n equals a sub 1 plus n minus 1 times d. That formula works too, but it assumes that you're starting at 1. So this formula is when you start at 1. This formula, though, is when you start at 0, like we're doing right now. So I use this form. Okay, so in this case, a sub n will be a sub 0, which is 1 plus n times the difference between the numbers, which is 2. So a sub n should be 2n plus 1. Okay, and you can check that that creates 1, 3, 5, 7, etc. So if you put in 0 for 2n plus 1, you get 1. If you plug in 1, you get 3. So it works, and I'm going to need a little more room for my boxes, right? Okay, so it should be 2n plus 1, and this is 2n plus 1, and this, it's all the same, right? Because they're all 3's. If you want, they're all 1's here. And then they're all 3's, and then they're all 5's. Then they're all 7's, etc. Right? So that's your summation notation if they ask for it. On a test, I'm happy if you just put this thing here. You could just put the polynomial. But working with summation notation is a nice extra skill to have for math. So if you can, try to get it into that summation notation. You may have to for the homework, but like I said on the test, this is fine. Okay, so there is our power series representation for this guy. You can show that the interval of convergence is all real numbers using the ratio test. We're going to skip that part. One thing to notice here is I keep saying it's the power series representation, and I kind of promised that these things would be equal to each other somehow. So if you take basically the limit of this thing is basically the limit of a bunch of Mclaurin polynomials, right? And I'm trying to say that thing converges to sine of 3x. Exactly, those things are equal. So why am I keep saying that this is a power series representation? Well, I kind of suggested that in the previous video when I was talking about this thing, f of x equals sine of x, versus this other guy, f of x equals this thing, let's say -1 if x is less than negative pi over 2, and then just sine of x if x is greater than or equal to negative pi over 2. Okay. So sine of x, of course, its graph is periodic and it keeps on going like this. This other graph, though, is a little different, right? It looks the same around c equals 0, but then when you get over here to the left, it just goes -1. Okay. So the trouble with the power series representation of sine of x is that the polynomials, the limit of the polynomials will conform to this. Just because of the way we've created it. I mean, think about the power series representation. F of x will be f of 0 plus f prime of 0. So it's not really dependent on values out here or values out here. Okay, it's only dependent on this value in the middle, this center. Right. So f of x over, I guess it's 1 factorial. F prime of 0 times I plus f double prime of 0 all over 2 factorial x squared, etc. Right? So you really don't need to know anything about the function out at the other edges. So if you have a function like the second guy here, and you look outwards away from the center, it's different, right? You could even take a graphical kind of look at what's happening with our power series. So maybe if you go in the Desmos, we can kind of take a look at that graphing and see how this is working with sequences of polynomials. So we know the power series for sine of x, or maybe we should do, no, let's do sine of x. So sine of x is equal to, literally, what is it equal to? If you go through the process, it'll be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, etc. Let's look at that as a sort of a sequence of functions and see how it kind of conforms to sine of x, even though it only knows how sine of x works in the middle. You construct the power series based off of how it behaves at the center, right? So, okay, so let's look at this. And maybe we should put sine of x in there first, right? Okay, so x is the first one, x minus x cubed over, okay, it's going to be a jerk, x cubed over 3 factorial. Okay, and you see how that green one kind of conforms. And what you're going to see is that the sequence of polynomials is getting closer and closer to the sine of x, but it's kind of a spreading out from the middle. Okay, okay, so let's look at x to the third all over 3 factorial plus x to the fifth all over 5 factorial. Okay. X minus x cubed. Sorry, let's just see if I can copy and paste, right? It's not going to let me do that. Minus x to the 7th all over 7 factorial. So sort of getting the idea of what's going on here. I mean, it's based off of just, you know, to create the other power series, so to create the power series for this other weird looking guy where it has this portion, you're going to end up with this power series, just because of the way the thing is defined. You never kind of ever look at this part of it if you're going to do the power series. So, although you can have something converging, you know, you have this limit of polynomials, and you know, it may converge in some interval. It may not converge to the actual function. Okay, so you kind of have to always say it's the power series representation. But in general, these things will converge to the function unless you're dealing with something weird. Okay, something that we're not familiar with as Calc 2 students. So, anyways. In order to show that the sequence of polynomials is actually equal to the function it's representing, we have theorem 9.23, I believe. And basically it says if that remainder function that we had from our Taylor inequality that we were using to determine how good the polynomial approximations were, if you take that thing and you take the limit as n goes to infinity, and that thing ends up equaling 0 for all x in some interval, then you can conclude that the function and the power series representation are the same things. Okay. So if the limit of that remainder function is 0 for all x in some interval I, then the Taylor series representation for f converges and equals the function it was representing. Okay, so we want to go through and at least prove this to you once. We want to prove this for sine of x, and then we'll kind of usually just take it for granted. Okay, okay. So let's prove this for sine x. Show the Mclaren series representation for sine of x is equal to sine of x for all x. Okay. Okay. So what is the Mclaren series representation? I'll just give it to you at this point. we note sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot dot dot. If you want the summation notation, it's n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 all over 2n plus 1 factorial. Okay. Let's think about our remainder thing. So recall how that thing worked. We had r sub n of x is, because it's an absolute value, it's definitely greater than or equal to 0, but then it's also less than or equal to this f, the max of the absolute value of the n plus first derivative on this interval, and here it's the infinite interval on the real numbers, and then times x to the, or actually it's x minus 0, but then x to the n plus 1 and absolute values all over n plus 1 factorial. Okay, so hopefully you kind of remember seeing that scary looking thing. We want to show the limit of r sub n of x is equal to 0 as n goes to infinity. And what we're going to do is kind of the squeeze theorem. We're going to kind of, we will use the squeeze theorem. So let me kind of give you an overview of what we're going to do. We will use the squeeze theorem to show that the limit of the left-hand side, which is 0, equals 0, and that will equal the limit of the right-hand side. Okay, so let me rewrite the right-hand side as the max of the n plus first derivative on this interval times x to the, well, I guess there's nothing to rewrite, right? It is just kind of what it is. So I'm going to be taking the limit of that right-hand side. I just trying to avoid writing it out. So this is the max of the n plus first derivative all over n plus 1 factorial times absolute value of x to the n. This one. We want to show that those two are equal to each other, and hence this will force the limit of the absolute value of r sub n of x to equal 0. And we had actually a theorem in 9.1 that said if the limit of the absolute value of the terms is equal to 0, then the limit of the regular terms is equal to 0. So then, because of the absolute value theorem, which is what we called it, absolute value theorem for limits, and I believe that was 9.1, we have that the limit of r sub n of x will equal 0. Okay, so the troublemaker here is this guy right here, trying to show that this thing equals 0. The limit of 0 clearly is 0. So on this side, the left side, we're kind of done. It's this right-hand side that we need to worry about. So the first thing I'm going to kind of get off my plate is just dealing with the maximum of the n plus first derivative. And that turns out to be pretty easy because we're dealing with a sine function. Okay. So firstly, notice that the absolute value of the n plus first derivative of x is going to equal one of two things, right? It's either going to be sine of x or it's going to be cosine of x. In either case, the maximum will be 1. So we could say the maximum of the n plus first derivative of x on the real numbers is going to equal 1. Okay. Hence, we may write, or we may rewrite the right-hand side of that above inequality that I marked off in here in red. Or we may rewrite, and let's just kind of do that. You may rewrite the absolute value of r to the n of x. Whoops, not that. That's not the thing we want. We want let's say we may rewrite the right side of the above inequality as, so what do we have? As follows. We have the max of the absolute value of the n plus first derivative of x all over n plus 1 factorial times the absolute value of x to the n plus 1. We'll just rewrite that as absolute value of x to the n plus 1 all over n plus 1 factorial. Okay. And this is the thing then we're trying to get the limit of that thing. Okay. If we get the limit of that thing, that will be basically the limit of this thing in the red box up here. And we're hoping that's 0. Okay, I don't know if it is, but we're hoping. Okay, so how do we pull this off? So we're going to have to use, in a weird sort of way, the nth term test for divergence. Okay, so recall the nth term test for divergence. Okay. And what did that say? That said, if the limit of a sub n, the terms of the series did not equal 0, then the series a sub n was divergent. Okay. The contrapositive statement of that, so if you remember what a contrapositive is, from logic, if you have a statement, if P, then Q, the contrapositive is, if not Q, then P, not P. Okay? And those are logically equivalent. So we can rewrite this just using purely logic, no math involved. And so I reverse the direction of the implication, and then I negate both statements. So instead of, I'll start off with the second part. Okay. And instead of saying divergent, I say convergent. So I say if the series a sub n is convergent, then, and now I go to the first part, and I have to negate that part, right? Then the limit of a sub n does equal 0. Okay. Okay, so in other words, if I can show that the series that has these terms that I'm encircling in the blue box, in the blue circle, if I can show that the series that has those terms is convergent, then that means the limit of that thing in the blue circle is 0. And that's what I'm trying to show, right? I'm trying to show that right-hand side goes to 0, and then the Squeeze theorem, we could say that the limit of the absolute value of r sub n goes to 0, and then by the absolute value theorem, the limit of r sub n of x itself will go to 0, and that proves that sine of x is equal to its sequence of polynomials, these Mclaren polynomials. Okay, it's power series representation. Okay, so so then consider this series. So consider the series absolute value of x to the n plus 1 all over n plus 1 factorial from n equals 0 to infinity. Apply the ratio test. So the ratio test, we need an r value, which will be the limit of the absolute value of the terms of that series, a sub n plus 1 version. So x to the n plus 1 is n plus 2, all over n plus 1 factorial is n plus 2 factorial, times the reciprocal of a sub n, which will be n plus 1 factorial, divided by the absolute value of x to the n plus 1. Simplifying that, we get the limit of the absolute value of x to the first power all over n plus 2. Okay. And then what is that equal to? Well, that's equal to, well, you can factor out the x if you need to, bringing along the absolute value. Then you just have the limit of 1 over n plus 2 as n goes to infinity. That thing is absolutely equal to 0 for all x. In other words, the series is convergent for all x. And then by the contrapositive of the nth term test for divergence, the limit of the absolute value of x to the n plus 1 all over n plus 1 factorial is equal to 0. Hence, by the Squeeze theorem, the limit of the absolute value of r sub n of x is equal to 0. Hence, by the absolute value theorem, for limits, I'll just say AVTL, the limit of r sub n of x is equal to 0. Hence, sine of x is equal to its power series representation. And that's it. Okay. Okay, so it is kind of a hassle to pull this off, but there it is. Okay. One thing that sort of to the side here is the binomial series. And I see this used often in advanced calculus when you're doing a lot more with the inequalities. So if you remember working with all the inequalities and doing the little proofs previously in this chapter 9, if you take advanced calculus, you use the binomial series expansion to do some of those little proofs in the beginning. So it's kind of nice to be a little bit familiar with it. But anyways, we can use it to get representations for things like 1 over the square root of 1 minus x. Okay, so let's go ahead and take a look at the binomial series. Representation for 1 plus x to the k value. Okay, so we're going to build this in the same way that we've been building our other polynomials and now series. So I'll start out with f of x equals 1 plus x to the k. This is centered at 0, by the way. And then I'm just going to get a bunch of derivatives and kind of look for a pattern. Okay. See how many derivatives I want. Trying to get my pen to work. And over here, I'll get f of 0. And then if I can get a pattern out of that, that would be nice. Okay. So taking derivatives, you bring down the k, and then it's 1 plus x to the k minus 1. No chain rule. So if you do the chain rule, the derivative of 1 plus x is just 1, so nothing to worry about there. This will be k times k minus 1 times 1 plus x to the k minus 2. This will be k times k minus 1 times k minus 2 times 1 plus x to the k minus 3. This is k times k minus 1 times k minus 2 times k minus 3 times 1 plus x to the k minus 4. If you plug in 0 for each one, you're just always going to get 1 from that 1 plus x to the k part, or 1 plus x to the k minus 1. So that'll be 1, this will be k times k minus 1, this will be k times k minus 1, times k minus 2, this will be k times k minus 1 times k minus 2 times k minus 3. Okay. So it's kind of like a factorial, but not quite. Okay, so there's not going to be a nice way to kind of write this out that we are familiar with. You can use, if you are familiar with more probability and stuff like that, you can use the n choose k notation. Most of us aren't familiar with that, so we're just going to kind of fake it. So what's the pattern here? It's going k times k minus 1 times k minus 2 all the way down to k minus something in terms of n, right? So I kind of look for the pattern. When it's 2, it goes down to 1, right? When it's 3, the last number here is 2. When it's 4, the last number here is 3. Okay, so when it's n, the last number here is n minus 1. Okay, so let's kind of dump that into our Maclaurin series representation. So f of x will be, blank plus blank times x plus blank times x squared over 2 factorial plus blank times x cubed over 3 factorial plus blah, blah, blah. Okay, so the first one is 1, and then we get k, and then we get k times k minus 1, and then k times k minus 1, k minus 2. And in general, if you want the summation notation, it's sum from n equals 0 to infinity of k times k minus 1 times k minus 2, dot, 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 all the way to the k minus n minus 1, x to the n all over n factorial. Okay. I think that's it. And that formula doesn't work for small values of n. I'm just looking at that right now. So so you really have to go like 1 plus this to get that first term. Otherwise, you're not going to be able to get it. Let's see if it works for the second term. So I have to start at 1, right? So n equals 1. Okay, so we k minus 1 minus 1, 1 minus 1, 0, so it's just k, x to the 1 all over 1 factorial, then it works. Okay, so there's that. So what? And also this thing converges on what interval, so we'll just give that to you, converges on the interval from -1 to 1. Okay. Okay. So what? Well, that's going to allow you to do Maclaurin series for things like this: f of x equals 1 all over the square root of 1 minus x. As far as inequalities go, if you ever have the misfortune of taking like advanced calculus, not that that's a bad thing, but some people, it drive them crazy probably. You can use this to kind of, if you have anything like 1 plus x to the 1/2 power, you can say that at least in that interval, it'll be greater than or equal to 1 plus 1/2 x. Okay, so you can kind of make these type of inequalities, which turns out to be useful for whatever reason. later on in the math universe. Okay, so anyways, let's look at an application relevant to us. So how do I get this thing? You can rewrite it as 1 all over 1 minus x to the 1/2. And then you could rewrite that as 1 minus x to the negative 1/2. Okay. Okay, so then it's not even a matter of having to go through and do your chart. You could just sort of plug and chug into the original template. So let me zoom out a little bit here, and note we're letting k be negative 1/2, and then x is being rewritten as negative x because it's 1 minus x, and originally this is the power series rep for 1 plus x to the k. All right. So you just replace x with negative x and k with negative 1/2, and so our power series representation will be 1 plus negative 1/2 times negative x plus negative 1/2 times negative 1/2 minus 1 is negative 3/2 times x squared all over 2 factorial, and it would be negative x squared, right? Plus negative 1/2 times negative 3/2 times negative 5/2 times negative x cubed all over 3 factorial plus ... And we'll just leave it in this form. We won't get the summation notation for this one. So this will be, notice all the terms are going to be positive because of the way it's sort of panning out. So this will be 1 plus x over 2 plus 3 times 1 times x squared all over 2 squared times 2 factorial plus 5 times 3 times 1 times x cubed all over 2 cubed times 3 factorial. You kind of see the pattern if you needed to go to the summation notation. We might as well do the summation notation. So this next one, 7 times 5 times 3 times 1 times x to the 4th all over 2 to the 4th times 4 factorial. Okay, blah, blah, blah. And of course that will equal the sum from probably n equals 1, so we'll go 1 plus n equals 1 to infinity of, what is that? How do I get the sequence 1? So 1, 3, 5, 7, right? So we want 1, 3, 5, 7, starting with n equals 1. So our formula a sub n equals a sub 1 plus n minus 1 times the difference, which in this case is 2. So a sub n equals 1 plus 2n minus 2. So a sub n is going to be 2n minus 1. So it'll be 2n minus 1 times 2n minus, it always goes down by 2 when you do this. So 2n minus 3 ... to 3 times 1 times x to the, and that'll just be n because it's going 1, 2, 3. Those exponents are going 1, 2, 3, 4, and all the other numbers are moving by the same amount, right? Whoops, sorry. It's 2 to some power, right? So 2 to the 1, 2 to the 2. So also this is going 1, 2, 3, 4. So that'll just be n. And then the factorials are going in the same way, right? You don't see the 1 factorial, but you can pretend it's there. So you got 1 factorial, 2 factorial, 3 factorial. So in general, n factorial. And that would be your summation notation if you were so ambitious. Okay. Once you kind of have, once you've kind of worked with these enough, you worked with enough Taylor series, believe it or not, you would have memorized after a while And then you could just kind of make up new series from a list of old series by doing substitutions and taking integrals, taking derivatives. So there is a table in the book that you can reference as you go through this last section once you've kind of mastered the process. Okay. So let's take a look at that. I want to find the page number for you. So sorry, 1 second. It's on page 674. So this is deriving series from a list of series, section 3, using the table of power series representations. And the table is on, again, page 674. It doesn't matter what edition you have. It'll be in there. Chapter 9 point whatever, 10 now. I'm going to remind myself to give you the video quiz here. Okay. So let's make this one the video quiz. We have an example, video quiz, video quiz, video quiz. Let me mark this down in my notes so I knew I did it because I keep forgetting. So this will be the last problem in homework number 8. There's only 2 questions in homework number 8. Okay. And basically you have to find the Mclaren series representation for e to the 6x. Okay, but the deal is you don't want to have to go through finding all the derivatives and then getting all the derivatives evaluated at their center and then plopping into the. You don't want to do that. You want to do it kind of like we did the binomial. Okay, so we have a template. In this case, the templates are in this table on page 674. And what you're going to do is just a substitution. Okay, so from the template, if you look in the book, e to the x is just going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus dot dot dot. If you can just do that. If you like the summation notation better, you can use that. This will be n equals 0 to infinity of x to the n over n factorial. Okay. So to get e to the 6x, all you need to do is substitute in 6x for x. Okay. So you get 1 plus 6x plus 6x squared over 2 factorial plus 6x cubed over 3 factorial. It's like, why reinvent the wheel, right? 4 over 4 factorial plus dot dot dot. And then in your summation notation, that will be just put in 6x for x over n factorial, and that's pretty much it. Easy, right? And if you want to, you can rewrite that as sum 6 to the n times x to the n all over n factorial from n equals 0 to infinity. Okay. There it is. Video quiz, video quiz, video quiz. Okay. For more complicated functions, so when you have products of functions or quotients of functions, you can actually divide and multiply the power series. And in general, you're not going to look for the whole power series. You're just going to look for the kind of first couple terms. And sometimes this will, if you take like differential equations, you'll have to work with power series. Sometimes, depends on your teacher. But let's take a look at this real quick, just so I know that you've seen it before. Multiplication and division. I'm just going to look at the multiplication version. The division works just like long division, except the polynomials are infinitely long. So let's look at this example. F of x is e to the x times sine of x. Okay, so the way I'm going to do it is write the representation for e to the x. Okay, you can go to your table and get this. Where you can sit there and figure it out, right? You can get the derivatives and plop them into the sort of template for the power series. In this problem, all they want are the first 4 terms, first 4 non-zero terms. Okay. Then sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th. Oops, that should be minus. It has alternating signs. I don't think we need to go up that far, but we'll see. Okay, and then you just multiply them like you did in algebra, right? So it's like a big distribution, so it'll be this x times 1 times that, times etc. Okay, so in that first distribution, you'll have x plus x squared plus x cubed over 2 factorial plus x to the 4th over 3 factorial plus x to the 5th over 4 factorial. And just go long enough so you think you're going to pop out the first 4 non-zero terms. Worst comes to worst, you can add a couple in where the dots are. Okay, so that's the first term. Then you go on to your second term and distribute that through. Okay. So this time x cubed times 1, and then you line up the powers because that's where you're going to be doing your addition. So x cubed over 3 factorial times 1, negative x cubed over 3 factorial, and then minus, that'll be x to the 4th over 3. So you're going to get a cancellation there. So you're going to at least need to go up to the 5th power here. X minus x to the 3 times x to the 2 is x to the 5 all over 3 factorial times 2 factorial. Okay. Let's go on to the next one. The x to the 5th, and you're kind of distributing that thing. I don't need too many of them. X to the 5th, yeah, so I need the first one. X to the 5th over 5 factorial. And of course these go on and on. If we need to, we can add more in. Okay. But for now, I think that's going to be enough to get us the first 4 terms. So now you're just adding, this way. Okay. Okay, so the first term is x, and then we have an x squared, and then this term, so 3 factorial is 6, 2 factorial is just 2. I'm going to need to multiply top and bottom by 3 to get the common denominator. So that will be 3 over 6 minus 1 over 6, which is 2 over 6, which is 1 over 3. Okay. These will cancel each other out, so that's just a 0 in that position. So I need to go to this third one and see if that gives me anything. 5 factorial is 120. 3 factorial is 6 times 2 is 12. 4 factorial is 24. Okay. So to get 24 here, I need to multiply by 2 on top and bottom. And then I need a 120, so I need to multiply them both by 5 and top and bottom. So if I multiply this by 5, I'll get 120. This by 5, I'll get negative 10. This by 5, I get 120. And this by 5 up here. So I get negative 5 over 120, negative 4 over 120, which is negative 1 all over 30, so negative x to the 5th over 30, and that just keeps on going, right? Okay, so those are the first 4 terms of the power series representation for e to the x times sine x. Now you can imagine having to find all those derivatives. There's going to be product rules, and it's just going to be a real nightmare. Okay, so anyways, the kind of cool thing now that we can do, maybe I should have made this one the video quiz, I didn't, but the cool thing now is we can actually figure out approximations for these integrals that we couldn't necessarily do before. Okay, so approximating integrals. So for example here, the integral of e to the negative x cubed from 0 to 1. There's no way you're going to be able to do this just sort of using U subs or anything like that. It won't work. We know how to do approximations, but let's do it using the Maclaurin power series. Okay, so first off, we need a power series representation for this e to the negative x cubed, and so again, I'm going to do a substitution method. Okay, so e to the x again is 1 plus x squared, etc. Okay. Then e to the negative x cubed, I'm just going to replace x with negative x cubed. So get 1, this will be minus x cubed, plus negative x cubed squared will be x to the 6. Then negative x cubed cubed will be x to the 9th. And of course there's a negative in there. When you cube a negative, it'll be negative. Then this will be plus x to the 12th. You're just multiplying exponents. Minus dot dot dot. Okay. Okay. If you want the power series representation to work with, this power series, of course, is x to the n all over n factorial from n equals 0 to infinity. This power series, you're just putting negative x cubed in there. So negative x cubed to the n all over n factorial from n is 0 to infinity, which of course is the summation of negative 1 to the n times x to the 3n all over n factorial from n equals 0 to infinity. Okay? Okay, so we need to integrate that. So here we go. Integral from 0 to 1 of e to negative x cubed dx will be the integral from 0 to 1 of the sum of negative 1 to the n x to the 3n, or if you want to, you just put the polynomial in there. N equals 0 to infinity dx. So this thing will equal, in summation notation, and it might be a good idea to get summation notation because we need to kind of work with an estimation theorem. So you need kind of that formula for the terms of the series. But anyways, this will be something to infinity. Maybe I shouldn't put the lower limit in yet. So this will be negative 1, and you're taking the integral of x to the 3n, right? So it'll be x to the 3n plus 1 all over, let's put the n factorial first. N factorial times 3n plus 1. Okay, evaluated from 0 to 1. And then if we put in 1 for x, of course we just get the sum from n equals whatever to infinity of negative 1 times to the n times 1 all over n factorial times 3n plus 1. And then minus, when you plug in 0, all the terms will be 0. Let's make sure we get the lower limit correct. Okay, so if we were to integrate each of these, the first term, and going term by terms, working with this expression, the first term would be x, the next one would be x to the 4th over 4, and then plus x to the 7th all over 2 factorial times 7, minus etc. Right? So we want to, and then you plug in 1, and it would be 1 minus 1 over 4. So this thing would be, as a polynomial, or a power series rather expanded, it's 1 minus 1 to the 4th over 4 plus 1 to the 7th all over 2 factorial times 7. Let's look at a bunch of terms out here. Then 1 all over 3 factorial times, what's the pattern here? It's going by 3n plus 1, so n equals the first one, the second one should be 1, so it's got to be 0, right? Second one would be 1, and then this is 2, and then 3 would give me 10, plus 1 all over 4 factorial times 13, right? And on and on. Okay, so anyways, that's kind. You could kind of figure out what an approximation using this. We want to make our approximation less than 0.001. In other words, we want the difference between the actual integral and this approximation to be less than 0.0001. Okay, and we're going to use the alternating series estimation theorem to do this because this is actually an alternating series if you look at it. The terms in the denominator are increasing, therefore the terms of this series are decreasing, and the limit of those terms will go to 0. Okay, so we desire, and this was given in the book, this part, we desire this approximation to be less than 0.001. We use the alternating series estimation theorem to determine the number of terms we need for this amount of error. Okay, so if you remember so recall what that was. It's s minus s sub n is less than or equal to a sub n plus 1, and we want that to be less than 0.0001. Okay. The formula for a sub n is kind of right here. This is -1 times a sub n, right? So the formula for a sub n is 1 over n factorial times 3n plus 1. And we want a sub n plus 1. And a sub n plus 1 will be 1 all over n plus 1 factorial times 3 times n plus 1, which will equal 1 all over n plus 1 factorial times 3n plus 3 plus 1 is 3n plus 4. And then you're going to have to do trial and error until this thing goes below 0.0001. Okay? So by trial and error, we note n equaling 0 gives us 1 all over 1 factorial is 1 times 4, 0.25. That's not good enough. N equals 1 gives us 1 all over 2 factorial times 7, which will be 1/14, which will be 0.0714-ish, which is not good enough. N is 2 gives us 1 all over 3 factorial 6 times 10. So it's 1/60th, which is 0.016 repeating. Try n is 3. So we'll have 1 all over 4 factorial, which is 24, times 12. Oops. So 12. 9 plus 4 is 13. Sorry. Which will equal 0.0032. Still not good enough. N equals 4. Get 1 all over, just put 5 factorial times, so we're putting in 4, 12, 16, which is 0.000 almost, so it must be n equals 5. So we have then 1 all over 6 factorial times 19, which will be 0.00007, which is definitely less than the 0.0001 that we wanted. Hence, we can approximate the integral with the first 5 terms that you see. Okay? So you kind of forget about s sub 1, s sub 0, where you're starting, and just basically, if this says 5, use the first 5 terms. Okay? And you're going to see that this is the term that's not going to be there. Okay, so what am I saying? We can approximate e to the negative x cubed from 0 to 1 by just using the first 5 terms that you kind of see. It's basically, this is your answer here. 1, 2, 3, 4, 5. The next term would be that term that we produced here. Okay, this 1 over 6 factorial. If you kept on going, that would be the one that would be next. 1 all over 6 no, it's not. 1, 2, 3, 4. Am I missing one? 5. Well, I'm going to need this 2 more actually then. Okay. So the next one is 1 all over 5 factorial times 16. And the next one would be the 1 all over the 6 factorial times 19. So the way it works is that you add up everything that's before the one that is good. Okay, so we found this one to be less than 0.0001. So what you do for your answer is just take all the terms that come before it. Okay, that way you don't have to worry about, did I start at 0 or did I start at 1? And so does n equal 5 represent the first 6 terms, or does it represent the first 5 terms? Okay, you could void it just by writing out the first many terms, and basically your approximation will be everything that comes before the a sub n plus 1 term that works. See, everything that came before this guy will be your approximation. So you'll have 1 minus 1 over 4 plus 1 all over 7 times 2 factorial minus 1 all over 10 times 3 factorial plus 1 all over 13 times 4 factorial minus 1 all over 16 times 5 factorial, and then you stop because the next term will be the one that works. Okay, so hopefully that makes some sense. And we'll call it quits for this video, and we'll see you next. Well, I guess I'll be doing a review next, and then one more chapter, and we're all done with Calc 2. All right, thanks for watching. See you next time.